What is going on, everybody? It's your boy Average Leader here, coming at you with another video. Today we're tackling minimum night moves number 1197 on Leetcode. It's commonly asked by Mathworks, Facebook, DoorDash, Amazon, Google, and a few other companies. So without further ado, let's get right into it. In an infinite chessboard with coordinates from -infinity to +infinity, you have a knight at square 0, 0. Okay, so this is important. -infinity to +infinity, there's no bounds, but we have a knight starting at 0, 0. A knight has 8 possible moves it can make, as illustrated below. Each move is 2 squares in the cardinal direction, and then 1 square in the orthogonal direction. So basically any L shape from its current position. So this L, this L, this L, and so on and so forth. Return the minimum number of steps needed to move the knight to square xy. It is guaranteed the answer exists. Okay, so off the bat, this is screaming, do a breath first search. And the reason I say that is because we're asked to return the minimum number of steps, or the minimum path between two known locations, or two known positions. So basically, if we're given a starting position, which we know the knight is at 0, 0, and an ending position, which we will be given through our parameters x, y, and we're asked to get the minimum path in between, this is a very standard BFS question. So we'll just start from our current position, and we'll search on every single position or coordinate that is L shape away, that is an L shape away, okay? And after we do that, we'll just go to that position and then go another L away. And then from that position, another L away, until we find our target X and Y. So let's get right into coding this thing. So what are we returning? Well, returning the number of moves. So let's make a moves variable, and I'll just make it 0 in the beginning. And for a BFS, we typically will use a queue. So I guess the question is, what are we storing in this queue? Well, everything is given to us in XY coordinates. We have like a starting coordinate of 0, 0. We have an ending coordinate of like XY. So let's just maybe store some coordinates in our queue. And I think that makes sense, because when we go search for like the next possible XY coordinate, XY pairing, it'll just be easy to hold a coordinate. So how can we actually do that? I think a very easy way to do it is by making a coordinate class. So that would look something like class coordinate, oops, my bad, not that. And in the class, we'll have 2 instance variables. We'll have an X position and then a Y position, and then we'll have a constructor that will assign our X position, Y position to whatever we want it to be. So let's go ahead and do that here. It's Y, and we'll do this dot X equals X and this dot Y equals Y. So remember, this dot X is referring to this instance variable, or the coordinates, our coordinates X variable, and this X is like whatever we're passing in. So we're setting our coordinates X to whatever we're passing, and we're doing the same thing for the Y, okay? So now we have our coordinate class, okay? So let's go ahead. This queue is gonna store coordinates, and we will initialize it to be a new linked list. Remember, we can't initialize it to a queue because queue is an abstract data type, so we need to make it a linked list. And awesome. So what is gonna be the very first thing we put into our queue? Well, we're told that the knight will start at 0, 0, so let's go ahead and add coordinate 0, 0. So q.add new coordinate 0, 0. Awesome. So now, so now a typical BFS implementation would be, while this queue is not empty, we'd get the size of that queue and iterate through all the coordinates in that size. And for each of these coordinates we encounter, we'll add their neighbors, or any points that are an L away from that coordinate. We'll just add those to the queue. So that would look something like this. While the queue is not empty, we'll grab the size, and we're gonna reinitialize the size every time we're in our while loop. Oops, equals q.size. And we're going to iterate through everything that's in the size. So we'll do this by doing like a quick for loop for int I equals 0, I is less than size, I plus plus. Awesome. So we created this for loop to iterate through the neighbors, we created this for loop to iterate through everything that's in our queue and then find all of its neighbors. So how do we actually get these neighbors? Well, since we are working with XY coordinates, we know that to get to a neighbor point, we need to add 2 to all the cardinal directions as shown here in the instructions, and then 1 square to the orthogonal direction. So if we're traveling 2 squares left or right, then we know we're gonna have to go 1 square up or down, right, to actually simulate that L. And similarly, if we're going 1 square left and right, then we're gonna have to go 2 squares up or down to also simulate that shape of the L. So one way where we can kind of like simulate these or like hold these directions is by maybe utilizing some extra storage to hold these directions. So I can do that up here. And keep in mind, so in our directions, if we look at the x direction specifically, how many places can we go from our current position? Well, we can go -2 to the left, -1 to the left, +1 to the right, and +2 to the right. So let's just do that. In our x direction, this is gonna be an array of integers. We can go -2 to the left, -1 to the left, 1 to the right, and 2 to the right. And what direction can we go in our y? So while we're -2 right now, while we're -2 to the left, we can go up 1 or down 1. So basically, +1 in the y direction or -1 in the y direction. So let's just pair the -2 with a -1 and a +1. And the way I can do that is by adding 2 of each of these x directions. So we'll have 2 -2s, 2 -1s, and then 2 1s and 2 2s. And like I said, when we go in the -2 direction, we can go +1 in the y direction and -1 in the y direction. So that's exactly what I'm going to have here: -1, 1. And when we go -1 in the x direction, we can go +2 or -2 in the y direction. So I'm going to do that right here: -2, 2. And when we go 1, it's going to be very similar. We're going to go -2 and +2 in the y direction. So we'll just do that: -2, 2. And finally, we're going to go -1 and 1 in the y direction when we're going 2 to the right in the x direction. So perfect. Now we have all the directions that we can traverse through. Okay. So from our current point, we can get our current point by just popping off or like removing an element from the queue. So I can just do that by doing something like this: coordinate p equals equals q dot remove. And now we're gonna iterate through our x directions and our y directions and add each individual direction pair to our current coordinates x and y, and then add that new overall coordinate to our queue. So that's exactly what we're going to do. So I'm going to iterate through one of these arrays. I'll just iterate through the xdir equals 0, j is less than xdir dot length, j plus plus. And we are going to create like a new position or a new coordinate. So I'll just do int px, new px equals p dot x, which is going to get this p's x coordinate plus xdir I. So it's going to basically go through all of these x's and add that current direction to our current coordinates x position. And we're going to do the same thing with the y's. So p dot y plus ydir. We're going to index it in the I. Oh, my bad, not the I. It's got to be in the j because we have j here. So not I, j. Okay, great. Good thing I caught that. And we're going to add this new coordinate point, this new xy coordinate, to our queue. New coordinate, new px, new py. Awesome. And now, finally, remember, what are we trying to output? it's the minimum number of moves. So at some point, we know we have to increment this moves variable. So when would we do that? Well, by iterating through all the directions that could be added to all the coordinates in our queue, we are simulating one more move that could be made from our current position. So in other words, after we go through all the coordinates in our queue, or after iterating through, after going through this for loop, we can just add one to our moves. So finally, since we're returning the number of moves, when would be a good time to return like our moves? Well, if our coordinate that we're removing, if that x position and y position equals what's passed in, then we know that we are at the target position, the target coordinate location. So let's just do like a quick check. If px equals x and p.y equals y, we know we're at the target location. So let's just return the number of moves that was created or that were made to get to that position. And otherwise, like if we don't have another return statement up here, this is not going to compile. So this should, well, and since we know that the answer is always going to exist, this is going to be the return that's always going to trigger. But like for whatever reason, maybe we're just given like empty input or something like that, we'll just return -1. Okay, so this is how you do it, guys. So let's run it. Perfect. This is the first time on this channel that has actually worked. First time, so let's go ahead and submit this. And that is the video, guys. Let's just, thanks for watching.
They ask you how you are, you just have to say that you're fine when you're not really fine, but you just...
Oh, shoot. Oh, man, we got a time limit exceeded. Well, okay. Well, okay, so I guess, most of you guys can see that this wasn't necessarily the most efficient way we could do this, right? But, we're pretty close. I'll give you guys that. So, when we're given a BFS, how can we make this solution a little bit more efficient? When we're working with a search type problem, I think the easiest two efficiencies that we can make is, one, make sure we're not visiting the same coordinates over and over again. And two, try to maybe make our search space smaller. Okay, so those are the two efficiencies that we're going to keep in mind while we work through this problem. If we take some time to think about this and maybe visualize it, or if we draw this out, in our current implementation, we'll quickly see that many coordinates end up being visited a few times. And we're not caching any of these. So similar to my course schedule video, I think we need to find a way to keep track of all the coordinates that we visited so far, so we don't visit them again. And a quick way to do this is by adding maybe like a hash set or a visited set and storing these coordinates in the hash set and making sure that we only add coordinates that aren't in this visited set. Okay, so let's work with that first. So let me go ahead and do that. Now let me create a set here. And what would this hold? Well, it's going to be hard to store coordinates here because we need to figure out a way, like the contains method calls like the equals method. And, the equals method, we don't really have like an equals method in like our coordinate class or like meant for coordinates. We would have to overwrite that implementation. And I think that would just be like a little, cumbersome in a small, time period. So I think an easier way to do this, something that I always tend to go to, is just maybe let it hold strings or string. And I'll just like convert our coordinate into like a string. So I'll do something like this. Set visited equals new hash set. And I'll add since we have like our first coordinate at 0, 0, I'm going to add 0, 0. And this is going to be the representation of all my coordinates that I'm going to add in the visited set. I'm just going to have the x coordinate and then a comma and the y coordinate. Very, very straightforward. So where else would I need to add this, add coordinates to our visited set? Well, I would have to do it when I add something to the queue. So I'll also do visited.add. And see, we made this real nice and easy. We got the x coordinate, we got the y coordinate. So all we're going to do is new px, or just to make this even like as clear as possible. I'll just make like a new string and I'll call it s equals new px plus with a comma plus new py. And this, by just adding this string right here, this will convert this entire thing to a string. And now we'll add this s to our visited set. Now, when are we going to, now with the information that we were provided, like we just said, we're not going to add coordinates that are already in our visited set. So we'll do that. We'll make it a conditional while we're adding to the queue. So if, so if visited.contains, and you know what? I'm just going to move this string before it. I'm going to do it right there. So if it doesn't contain s, then we'll go ahead and add it to the queue and add it to our visited. So this is a quick efficiency to make this a tad bit better. And if we run it, I think this will work. But let's see if Leetcode will allow this. It's running. No, another time limit exceeded. Let's see, what tests have passed. It looks like all the tests have passed, but it's still taking a bit too long. So let's just think about one more way we can make this a little bit more efficient. So remember how I said earlier, another thing we could do is to make our search space a bit smaller. And just looking at our graph here, we see that it doesn't really matter like what direction you're going, or like it doesn't really matter if we are given a target of like a negative number or a positive number. In other words, if we had to go to -4, -2, that takes 2 moves to get to, right? We know it takes 2 moves to get there. But if we were going to +4, +2, that would take 2 moves to get there too. But if we had to go to +4, +2, our immediate directions that we're going towards is like in the negative direction based off of how we have it in our implementation. I do think it's important to go through the negative direction in case, for some moves we have to we have to jump a little bit forward and come backwards by utilizing this negative direction. But the key to this problem really is understanding that everything is symmetric. Or in other words, if we were given a positive x and a positive y, let's say 5, 5, and we were given a negative x and a positive y, or -5, 5, it'll take the same number of moves to get to both. So since knowing that, what if we just reduced our search space to just maybe like only positive numbers? That's like the quickest way to make our search space even smaller. So if we were given numbers -5, -5, or sorry, -4 and -2, we know it takes 2 moves. But if we just searched only in the first quadrant for +4, +2, and only looked in this top right quadrant, that will significantly cut out like a good chunk, 3/4 of our search space. So let's just do that. Let's only look at the positive values. So what if we were given negative values? Well, it's easy. We'll just take the absolute value of them. And that would look something like, we'll just do x equals math.abs x and y equals math.abs y. And we'll only look at the top right quadrant. So every time we're searching for a new px and a new py, let's make sure that that value remains in that top right quadrant. Or in other words, we can just check to see if px is greater than or equal to 0 and py is greater than or equal to 0. So, and new px is greater than or equal to 0, and new py is greater than or equal to 0. So let's just think about this. We've drastically cut out, we've cut out so much of the board. We're only looking at this top right quadrant. Let's just make sure that we're reaching all the points. It's time to test out our code, think of a few test cases that might possibly fail. So I'll give you guys a few seconds to think about that. Pause the video here and unpause whenever you guys are ready. But in this particular situation, is there any point where sometimes, because we are given the freedom of going in the negative direction, Could there be a space where it's smarter to go, or it takes less moves to go out of the board, or like out in the negative direction and then back into the positive direction? Well, let's just look at coordinate 1, 1 first. If we went to 1, 1 in our original code without by only constraining ourselves to the top right quadrant, we'll notice that it takes 4 moves to get there. But if we go outside of the board and then come back in, it'll take 2 moves. So let's just be a little bit, we'll just be a little bit lenient and recognize that there are a few spots on the board that require us to go outside of the board at least just 1 time. So at a max, it can go 2 spaces to the left or 2 spaces down. And anything after that, that'll just be more than 1 move outside of that first quadrant. So let's just be a little lenient here, and we'll say as long as our new px is a greater than or equal to -2, and as long as our new py is greater than or equal to -2, thus allowing ourselves to make 1 and only 1 move out of our bounds to go back in order to make maybe a bit of a better, more efficient solution. And let's see if this works. Okay, perfect. It passes that one. Let's see if that passes the whole. Perfect. Greater than 50% of Java. Runtime is better than 50%. Memory less than 48%. So let's talk about the runtime of this entire thing. I believe since we are not visiting already visited coordinates, then I think this would be O of n, where n is the number of moves we'd have to make. And our space complexity, well, since we're utilizing a queue in a visited set, which can also hold at max n moves, I think our space complexity is also O of n. And yeah, guys, that's how you do that problem. Let me know what you think. Let me know if this was helpful. This time around, I didn't go straight for the iPad. I coded it out how I thought of the problem, and then made it a little bit more efficient after that. Tried to kind of simulate how we'd go through in an interview. But yeah, let me know what you think. Let me know if there's a video you want me to do. And always, if you like this video, if you thought you found some value from this video, make sure to like and subscribe. Give me a comment. I'll make sure to respond back to you. And yeah, guys, I hope you guys have a good rest of the day.